set of people here. So we figured it would be a good idea to try and sort of create some common ground. So we'll start off with a welcome, and then I'm going to give a sort of background on the computer engineering, for lack of a better term, aspect of motivations for this conference. And then Arvind Murugan is going to give a short introduction to some of the maybe more fundamental science aspects of this conference. So first up, we have many people to thank. Amanda and Emily from the Aspen Center for Physics have been handling the logistics for this conference, and that's been a great pleasure for the scientific organizers, so that we have been able to absolve ourselves of any logistical responsibilities. So thanks very much to them and the rest of the staff here. I'd really like to thank the invited and the contributed speakers. And that sort of dovetails with everybody else as well for coming all this way to a conference that's never been organized before, that maybe you had no idea how well or badly this would go. Quite frankly, we don't yet either, but so far things are going well. So thank you all for making your way all your way out here, for committing to coming here. And we really look forward to the week or subset of the week together. We received a very strong response to the conference. We were really happy about this. We had over 170 people apply to attend, and the center capped us at 110 participants. So we're really enthusiastic about the response. We're really happy that you're all here. And we hope that this is a sign of the strength of the future of our broad field. I'd also like to thank everyone who brought posters. We have 2 poster sessions, and there will be food and drink catered during those sessions to really try and encourage people to stick around. And we hope that there'll be really interesting scientific discussions during those. Even though they're 2 sessions, we haven't divided the audience up into different days. If you brought a poster, please put it up as soon as possible, and you feel free to leave it up for the entire week. And you can pick any spot in the corridor outside that's not occupied by a fire extinguisher or something else like this. We also received a number of requests from people who were not able to make it, but who heard about the conference, that they would like to see the talks. And so we put together an ad hoc recording subcommittee that's comprised of people volunteered amongst our students and postdocs. And I'd really like to thank them, Mandar, who's chairing it, and then the others who have agreed to help out. Please be patient if things have snags. We are not professional AV people, but we're given the requests that we had, we think this will be a useful thing to do. We're only going to be doing it for the invited senior talks, just to sort of try and limit the workload. And if anyone wants to opt out, they should let us know. So let's now sort of give a broad sort of overview of what are the kind of things that we have here, and what are we hoping to cover. There's really 2 broad things that are being brought together at this conference. There's many people here who work on sort of fundamental aspects of computing with physical systems, that we could broadly maybe call the science. But there are also many people here who are very applied, who are thinking about how to engineer physical systems to do useful things for us. And the attendees span many different physical platforms. And the idea of having a conference that brings this all together is really that there are many people working on fundamental questions who we've realized often don't get to interact with the people on the very applied side, who may be trying to engineer new computers sort of in the relatively near future, and they probably have lots to learn from one another. There are many people doing work across different physical platforms, from CMOS electronics, rather traditional platform for computing, through to photonics, biological systems, mechanics, etc. And of course, in the disciplinary conferences, you often don't get to see the people from the other physical platforms, because things are often organized sort of by platform. And I think there's a lot of common work that's going on across these platforms. So hopefully there'll be many interesting discussions there across platforms. There's also, even sort of beyond just the choice of physical platform, many different motivations for why you, even in an applied sense, why you would want to try and compute with physical systems. There's people trying to sort of build computers to maybe replace what we have in CPUs and GPUs that I'll broadly call computer engineering, but there's also people very interested in sort of how do we do robotics or control systems with this. how do we build new biotechnologies and synthetic biology. And we're hopefully all here because we can learn from one another. And I'll make an appeal to the speakers. It's too late for the ones in the early morning session, or at least to modify slides. But for everyone else, please try to make your talks accessible. The reason I'm saying all of this is to a large extent to sort of just let you know, FYI, there's a very broad set of backgrounds here. And I think this it'll help a lot if people kind of make some effort to give a little bit more context than you normally would in your talks, and to be as careful as one can about jargon. Kind of emphasize this, I thought about trying to put together a Venn diagram of what just the senior invited speakers work on, never mind everybody else in the conference. I failed because it's too complicated to make a Venn diagram. And so this is what I ended up with. There are many people representing many different physical platforms, many different types of applications people are targeting. We have a healthy mix of theorists and experimentalists. And don't take the dashed lines too seriously because they're just what I think the invited speakers might talk about. But of course, we'll get to see later on in the week how correct these assumptions are. But this hopefully gives you a sense of, it's very broad, it's very nicely interconnected though. So I hope that there's lots for us to share. So with that, I'll head into giving sort of my perspective on computing with physical systems for computer engineering. And then, as I mentioned at the start, Arvind will give a sort of parallel talk on, or short introduction on the more fundamental side. So why are we even interested in trying to build computers that are faster or more energy efficient? At least to those of us who work in the field is obvious, but maybe just to sort of in the spirit of really setting the stage. I really like this graph as an example. I mean, in one word or two words, the answer would be machine learning. This plot shows the cost, in particular for training, of machine learning models over the last several decades. And particularly in the last decade here, you can see an enormous increase, the many orders of magnitude that the cost has increased by. And this really comes about from the fact that the models are getting larger and larger. And this has been really motivated by the fact that as you build your models to be larger, it turns out that they get more and more capabilities. So people have been really motivated to push this. This gives a massive challenge for people who build computers, because if we zoom in on this sort of last decade, you can see in the blue here that the model sizes and the cost of the models has been growing at this rate in blue, whereas Moore's law has been giving us this yellow trend. You can build specialized machines with digital processing and CMOS electronics that will give you a sort of one-time specialization boost. But there's this massive deficit that's growing. And so if we want to be able to continue the trends in at least the style of large models, it seems like we have to do something about this. Another sort of anecdote about this that I really like from a very recent paper that tried to quantify this was to work out how much energy does it cost to do various machine learning tasks, including some of the more popular generative modeling tasks that people are doing now with things like ChatGPT and DALL-E, for example, in image generation. So you can give a prompt and say, make me an image of the Aspen Center for Physics with physicists jumping around or whatever, and it'll make an image for you. How much does that cost in energy? I was shocked when I saw this table. I'm still not entirely convinced it's correct, but the paper, they did the analysis. They concluded that it costs about 3 kilowatt hours of energy, which is how much energy it takes to run like your household refrigerator for several hours. I mean, even if we didn't have the growth in the model sizes, this feels like this is reason enough for us to try and make the computers more efficient. So that's one sort of side of things. Another area that I'm really excited about that I think is really important is in sensing the physical world. There have been massive advances in sensors that we have, as everyone who has like a cell phone camera knows. You can take really nice high-resolution photographs. This has been repeated across essentially almost all areas of sensing, where the bandwidths are getting larger and larger. So we have a huge amount of sensing data, and then we have to do something about processing it. And this has become a major computing challenge. And in a recent SRC report, and they even sort of highlighted this as their very first so-called seismic shift, where they said, and they're motivating that maybe actually the way we should deal with this is not the way we're currently doing it, but by being inspired by biology, of sort of maybe trying to have some computation equivalent to in the retina, like happens in biological systems, that compresses the data before it goes on for further processing. And I think this is a really interesting area of applications for computing with physical systems, because if you're sensing the physical world, you can imagine that you can build a processor for the sensor that sort of operates in the same physical realm. If you have an optical signal, you can do optical processing. If you have a microwave signal, you can do microwave processing, etc. So how can we want to get large performance improvements? How can we do it? Well, there are a bunch of different techniques or strategies that are available that I think are relevant to our community. One is eliminating abstractions. So instead of trying to operate with deterministic digital logic signals, let's try work from the bottom up from physical system and operate with analog or probabilistic signals. I'll talk a little bit more about this in the next slide. We can do in-memory computing, which is essentially referring to breaking the so-called von Neumann bottleneck, which is this bottleneck where if you have a memory and a processor and you're trying to send data from the memory to the processor and back all the time, you get a bottleneck from the fact that the throughput between these two components is not as high as you would like, and it also leads to really large energy costs. And so the idea is to try to do computing in the memory array itself, so to speak. And I think this is something that's going to be very relevant to those of us who are trying to engineer computers out of physical systems. Another option that is sort of very relevant to most or many of us here is thinking about using alternative physical systems than standard CMOS electronics. Then finally, thinking about being tolerant to variations. If we imagine that we relax the requirement that every device that we have come out of our computer factory works exactly the same way, if we relax that, you can imagine getting large gains in efficiency. So I'll give a little bit more detail in closing on sort of what I mean by eliminating abstractions. So if we think about the sort of standard stack of abstractions in a computer that you learn about if you do a computer engineering degree, it's this beautiful stack of abstractions that's been developed over the past 50 years or so, where you start with some user application that gets programmed, built on top of algorithms, and you go from there through all these layers all the way down to the transistors. And the wonderful thing about this layer of abstractions is that if you're working on, let's say, the compilers, it's not actually so important that you know that much about how the transistors work, because the abstractions are very clean. The bad part of it is that because you forced each of these layers to have a very tight abstraction, you've given up certain amounts of efficiency or speed. So an alternative way to do it is by taking some physical system, it could even be CMOS transistors or some other unconventional hardware, and just identifying some hardware that has some complex dynamics, and then thinking about how to glue it together in a way that you can tune it and program it to do some task for you. So now the notion of the algorithm is almost directly tied with the physical dynamics of the hardware. And so you've eliminated all these abstractions, and in this way you can imagine getting an efficiency enhancement or a speed enhancement, but there's now lots of questions about how do you actually program this and build compilers for this and so on. So there's lots of work to do. As one example of this kind of what we mean by picking a physical system and making it into an algorithm for us, I'll just flash this up. There's a bunch of people working on building so-called icing machines, which are physical machines that solve optimization problems. Here's an example of two coupled oscillators that are coupled via these resistors. You could also have some networks of stochastic magnetic tunnel junctions that are connected in some network. And ultimately, what's happening in these systems is there's some dynamics given by, let's say, this differential equation here, or this discrete evolution equation here. The system evolves according to these dynamics, and the way you program the machine is by fiddling with the parameters that tell you how the different nodes are coupled. It's a very different notion of programming than usually. And Eli is going to give us a talk on this a little bit later in the morning. There's many different hardware platforms that you can imagine doing this in, and we have a good coverage of them at this conference. So I'm going to end off with some smattering of questions that I think are interesting in related to computer engineering. Just to give maybe the people who don't think about computer engineering all the time some sense of like what we care about, where at least we is what I thought of last night. So a major one is sort of what architecture should we use? How should we connect different physical components together to make it useful as a computer? physical system should we use? What are the trade-offs of different physical systems? Probably in almost all of these, the answer is going to be application dependent, because you may want to use optics when you have some optical image coming into your system, but you may want to use something else if it's an acoustic signal, for example. How can we harness the intrinsic computation that's done by a physical system? You give me a physical system, you know it's intrinsically doing a lot of computation, but how can you get it to do something useful for you? That's really tricky. Many of us are working on, for example, training systems to act as neural networks, but you can imagine this in all application domains. How do you deal with variations from device to device that you make and the noise in the devices? What are the right applications to target? What should we even be trying to make these special purpose machines for? Many of us are working on machine learning, but people are also in optimization here. There's also hope for being able to do things in scientific computing and maybe other applications as well. What are the right use cases? Should we be doing things that try to replace like something in your Apple Watch, or should we be doing things that replace something on the servers or on the cloud? Should we be doing sensor processing only? Should we be doing stored data processing, etc.? Major one for our field is how do we bridge the gap between where we are now and where we'd like to get to ultimately, of sort of beating the conventional systems. It's really tricky. A smaller topic in this conference, but there's some coverage of this, is how and when can quantumness of the physical system be useful? And then what are the fundamental and the practical limits to energy efficiency? How do we know we've gotten done as well as we can? And I think this is just a sort of, pretty incomplete and subjective list. So I hope that throughout the conference, other people will bring up other questions and we'll be able to discuss all of these. So with that, I'm going to hand over to Arvind. And thank you again all for coming. And I look forward to the discussions throughout the week.
Hear me through the microphone? Hey. Right. Well, I want to begin by thanking you for coming to probably the workshop with the biggest impedance mismatch I've seen between participants. In order to help a little bit with that, I would try and explain how Peter and I ended up with the same slide one of our talks, synthesizing many years of work in our groups, except we had never met and our motivations are very different. Peter obviously wants to build better computers. I'm in the physics department at Chicago, and for the last 7 or 8 years, our focus has been not so much building computers, but asking to what extent can molecular and mechanical systems learn to do information processing, learn to do certain computations, often with the biological motivation. And yet we ended up with the same slide. And I want to communicate to the more photonics and analog computing or electrical circuits-based people in this audience, why the more biological physics and soft matter people here care about the same things, even though the starting point is quite different. And that slide, how do I advance the slides? This is not that first slide, but there we go. So that slide that Peter and I converged on is something like this that he just went through. And you see, two ways of doing computation. The one at the top is what he alluded to as a sort of abstraction-heavy way of doing things. You solve a problem in the abstract, and as a consequence, forcing your hardware to play by the rules of some circuit you designed. But the other starting point is to just take the supermolecules, a complex disordered mechanical system, and just look at the many-body physics of what that system does. Phase transitions, instabilities, bifurcations, waves, whatever. And ask, it's doing this complex physics, but can you somehow harness that complex physics? Start from the physics first and ask, can you get that to do some computation you're interested in? In particular, when you get that system, you could either program it if you had a model of it, but if you don't have a model, can you get that system to learn the computation it should do just by physically experiencing examples of that behavior? Right? This is quite similar to what Peter laid out, but except why would you care about this with molecules and mechanics, which are pretty unlikely to ever make a competitive computer, right, with silicon? And the motivation, though, is quite similar, but comes from sort of a biological and physical point of view, which is this approach lets you do the same task with less. For example, in synthetic biology, big task to build sort of molecular devices that be deployed in many organisms or in many cell types in your body. And in each context, they need to do different things. That is, they need to sense the environment, some computation, and deploy different responses. You could do that with the abstracted way, but the idea is if you harness the natural physics, if you let molecules be molecules, you can achieve the same task with fewer parts. It'll be more robust. Because, for example, you won't need a molecule to be a sensor, another molecule to do a computation, the molecule to do a response. That'll be in one. But in fact, it's not just for synthetic biology. All these same reasons should also expect evolution to frequently tap into this kind of hidden computational ability just lying there for free rather than building an abstraction first circuit. Let me try and deepen that with one example of a common sort of stereotypical computational problem cells need to solve to survive. Imagine you're a cell and your environment is defined by, let's say, 20 things, 20 molecules. It's a 20-dimensional input space. pH, ATP, concentration levels of many RNA molecules. And in order to survive, you need to look at that input. And if it's in certain parts of 20-dimensional input space, you want to build structure one, molecular structure one, in order to survive that environment. For other inputs, you want to build structure two. It's essentially a classification problem. Cats and dogs, the neural network separates it. Here you're actually doing a functional response to survive. And yet, the success of systems biology convinced us, in some sense, took too much inspiration from engineering, and they convinced us the way you should expect this to be done is with a separate abstracted layer of computation, where essentially molecules role-play gates or neurons, linear threshold devices, forming a network, make a decision, right? There's a sensing layer, there's a computation layer, decision is made, and then the physics comes into play. There's an alternative perspective. It does the same thing with much less. And I'm going to use a kind of almost silly analogy, but it does hold in some sense. Here's the phase diagram for water. Abstractly, it's telling you what water molecules do as a function of two environmental inputs. Here it's pressure and temperature, but doesn't matter. It says in different parts of this input space, water builds different structures, ICE4, ICE3, ICE2, and so on. So in some sense, it's doing a computation for you as a function of two inputs. It's a phase diagram for water, but it's not special to water. All molecules, mechanical systems, in some sense, can be described, many body systems can be described by something like this. Key difference being when you take the complex molecular soups you have in cells, it's not a two-dimensional phase diagram, it's a 20-dimensional one. Those 20 axes are exactly these inputs. This is classic stuff that we've known for 70 years, this concept of phase transitions and phase diagrams. But if you take this perspective, this right-hand side is essentially solving the problem laid out here without any separation of sensing, actuation, and response. If only these phase boundaries can be placed where you want, what that phase diagram is telling you is for the right conditions, the system will do the right thing. Except with fewer components, because all of this is rolled into one, the structure built is the final structure. In some sense, with less energy, because it's a passive process where the energy, in some sense, comes from the input signal itself. The input signal carries the energy for the system. Right. And so for this reason, our idea is synthetic biology can work much better if we stop designing circuits and instead harness the collective physics of the system itself. For the same reason, you should expect to find this in natural systems. Evolution will go for these. Why do we not talk about this in textbooks? It's because these kinds of solutions are much harder for a biologist to spot or for anybody to spot because they're not modular. Parts don't have definite roles as a sensor and an actuator, and that makes it difficult to spot them. And so only by first working out conceptually what are the possible ways you could have this kind of embedded computation will we know how to even find them. Okay, all of this relies on the ability of programming these phase diagrams. Okay? may not distract you with this. How do you program this phase diagram? Well, much like Peter said, there are some interaction parameters in the system, and by changing them, you can program phase diagrams, not for water, but for multi-component systems. But often an evolution doesn't, evolution in some sense doesn't need this forward model. Synthetic biology, though, that's a problem. You don't often have a good forward model of the system. You have pretty bad forward models, but a lot of the physics is missing. That's where the idea of physical learning comes into play. Imagine just science fiction. You had a phase diagram like this, and you took ice in the water and you showed it examples of environments where you wanted to form ice 2 and examples of environments where you wanted to form ice 1. And while you showed it those examples in a period of training, there was some kind of molecular Hebbian learning going on, changing interactions of water parameters. You end up with this phase diagram as a consequence. That would be amazing, partly because that's impossible for water. But turns out it is possible for multi-component systems, not with one molecular species, but when you have 50 molecular species, it turns out this is possible through local simple rules. The idea is, again, that synthetic biology can exploit this by building one programmable circuit or trainable circuit that can go to different cell types, no forward model needed, and they get trained in situ to do different computations in different cell types. And it also, in the natural context, it provides an alternative to Darwinian evolution, short time scales for how do you acquire function by just seeing examples of the function in question. All that said, this is sort of just a perspective. All the work really remains to be done. Many open questions. I'm not going to go into the details, but I just want to lay them out as sort of two broad classes of questions. One set of questions, you forget about the training part for a second, ask, what about the physics of the system sets the complexity of the tasks you can do? Deep neural network can, is more expressive. It can sculpt decision boundaries in a more complex way. And we know that for neural networks, we know depth does that. What is the equivalent in a physical system? Does non-equilibrium dynamics help? Kinds of cooperativity helps. We don't know these things. And then, as I pointed out, if you want to have these systems train themselves, you're going to have to rely on the physical processes they have. They don't have backpropagation built in. You're going to have to rely on what they can naturally do. The question is, in different physical systems, what kinds of biologically plausible learning, Hebbian or contrastive, or the things can you get in physical systems that do exist? That I'll summarize again and say, even if you don't care about computers, the kind of theme physical computing is interesting, that it lets you do more with less, and it lets systems figure out for themselves what they should do, just seeing examples with no forward model or evolution needed. With that, I'll stop.